All right, guys. So this is our first one here, testing this out. So we're talking about section 4.7, indirect arguments, and we're going to be looking specifically at two classical theorems. These are two things that we know for sure. So our objectives in this section. Number one is we're going to look at the proof for the irrationality of square root of 2. Right? Something we know is true for sure, and we know why. And the other one we're going to look at is the question, are there actually infinite prime numbers? Prime numbers. That's not an N. Numbers. All right. So, just jumping right in here. So the theorem that we're looking at, I'll try and write bigger than that theorem moving forward. Maybe a little bigger here so it's not so blurry. I know the video quality is not that great. So, square root of 2 is irrational. So that's our theorem. So we're going to prove that. So of course we know square root of 2 is irrational because we can't write it as the ratio of two integers. And we're going to show that logically that is the case using my personal favorite, as we talked about, the indirect contradiction proof. So we're going to suppose not. That is, suppose square root of 2 is rational. So as always, thinking about what that means, what the conclusion of that is. So that means that there exists a and b in the integers such that square root of 2 equals a divided by b. Now in this particular proof, we do have to think about if a and b can be a over b, not a and b, but if a and over b can be reduced. So we're just going to add in a little without loss of generality. Assume a over b is fully reduced that way we don't have to build into our proof divide a and b by their greatest common factor. So we can assume that we know how to do that. So from here, we're going to look at the square root of 2 squared, and we know that that's going to be a over b squared, and so we have that 2 equals a squared over b squared. Or 2b squared equals a squared. So, since a is an integer, a squared is also an integer. Make sure we fit it in there. So we have then, since a squared is an integer, we can say that a squared, it follows that a squared is even, right? Because that's our definition of even, right? 2 times an integer. Oh wait, we want this to be b and this to be b. Make that switch. You'd think recording these I'd do better, but at least you know I'm being honest here, making the same errors I made during class. All right, so we know a squared is even. And the proof that we did in class last Thursday, we can then say, therefore, a is even. That was our contraposition proof we did on Thursday last week. So we have an even a. And so this means that there exists another integer k such that a equals 2k. And then a squared equals 2k quantity squared, which is 4k squared, and which we know from up here has to be 2b squared. So we're just going to divide both of these sides of our equation by 2 and get that 2k squared equals b squared. And again, since k is an integer, k squared is an integer also. So that means that now we have that b squared is even. So here's where it gets interesting. So we're going to come back and remember that we assumed that a over b was fully reduced already to start this proof, because we should be able to do that. So if b squared is even, then b is even. And then we can say that the square root of 2 equals a over b, which equals 2k over 2m. And this is for m an integer. Right, so we've already initialized k up here for a. We're just using m for b now. So, that up a bit. Let's see if I can get this in the same shot. Limited space on my desk. Wasn't designed for document cameras. Right, so then we have the square root of 2 equals k over m. And this means a and b are not fully reduced, and fully reduced, which of course is a contradiction. Now some of you might be wondering, well, how does that work if we said it was fully reduced? And the reason is, you can just look at this. So let's assume we didn't say it was fully reduced, and then we reduced it. We would get something like this, and now we can do the exact same trick we did to this equation, or that we did to this equation up here, to this new one, blue papers, to this one here. So we could square both sides, we get k squared over m squared equals 2. We go through the exact same process. So you can actually show that every single integer, if you allow square root of 2 to be rational, can be factored by 2, which we know is not possible because not every integer can do that. And you can repeat this process over and over and over again. And so that's why this statement is correct. We have fully reduced, or not fully reduced, and fully reduced, our contradiction. So it must be the case. Must be the case that square root of 2 is irrational. Goodness. Because if it is rational, basically what our proof is saying is that you can infinitely factor your rational number a over b, factor to k over m can factor into something like r over s, and this will just continue forever and ever and ever. And we know that's not true. Eventually we can't factor things anymore. So that's the proof for square root of 2 is irrational. So what we're going to do now is, instead of jumping straight into the primes, we're going to use this result, this theorem, to prove something else. Yeah, just a little bit interesting example. So this is the thing we're going to be doing, is prove that a plus b times the square root of 2 is irrational. Where a and b are arbitrary integers. So before I jump into this, I recommend you pause the video here and try and work this out, or at least get started on your own. And you can see how you were doing and whatnot. I'm going to say this for every example. Obviously, practice problems don't make sense when we're not working face-to-face. So pause the video here, give it a try. You're going to be using a very similar argument to our proof of rational numbers that we did last week on Thursday, with the addition of a rational and irrational must be irrational. It's a very similar proof to that, and then it's just going to hinge on that last theorem, that square root of 2 is irrational. So hopefully you're pausing the video now. So the proof. Again, I'm going to use a contradiction proof here. You can do this with a contraposition proof, but you know me, I love me some contradictions. So we're going to suppose not. That is, suppose that there exists an x and y in Z such that x plus y times the square root of 2 is in Q, is rational. So one thing I need to mention here, we just need one pair of x and y to work, because in our statement here, a and b are arbitrary integers, so that's implying that any integer should make this statement of a plus b rad 2 irrational, should make that statement true. So we just need to find the one pair that fails if we're supposing not. So it is an implied universally quantified statement here. Alright, so x plus y rad 2 in Q. This means then that there exists m and n in Z such that x plus y rad 2 equals m over n. So we're just going to subtract over the x. Y rad 2 equals m over n minus x, and then rad 2 equals m over n, y, make that a little longer, minus x over y. And the square root of 2 then equals mn minus mn? No, m nothing. M minus x times n, that's what it should be, all over supposed to be an n. Pretend that's an n. This is blurry enough that it looks like an n, so it'll work for you guys. So square root of 2 equals m minus xn over y. Now m, n, x, and y are in z. They're integers. So m minus xn is in z, and ny is in z. This means square root of 2 is rational. Which is a contradiction to the known theorem that the square root of 2 is irrational. So, must be the case. Be the case that a plus b rad 2, and I'm running out of space here, so I'm going to shorthand this as not in Q, not rational. And that's the end of the proof there. So just a fun little proof using the irrationality of 2. A lot of times when you're looking at is something rational or irrational, they'll go back to something like this and try and work square root of 2 into it because we know it's irrational. We can prove easily that other things, when they're manipulated with the square root of 2, are also irrational. Most things are. But again, something that we knew. So let's take a look at our next big theorem here. And that's talking about primes. So our theorem is that we set primes is infinite. Now we're not going to prove this just yet, because as it turns out, this proof requires the proof of another proposition first. So this is going to be a little example so you can see kind of, not a new technique, but a new way of proving or thinking about proving things, especially with primes and divisibility. So this is for any integer a and prime p. If p divides a, then p does not divide the quantity a plus 1. So again, before I jump into this, I recommend you pause the video here and try this out on your own and see how you do. I'm going to use a contradiction proof if that helps. So go ahead and try it on your own. Good job pausing the video, guys. I'm proud of you. So suppose not. So what we're really supposing is that there exists an integer a. Right? It just needs to be 1 because this is for any integer. So there exists an integer a and some prime p such that p divides a and p divides the quantity a plus 1. So using our definition, what happened to my b there? It looks weird. By definition, can I spell definition? Yes, possibly. There's an m and an n in z such that m times p equals a, because p divides a, and n times p equals a plus 1, since p also divides a plus 1. Remember, we don't want to use the same integers here because that would mean something very, very specific, and a is definitely not equal to a plus 1. So they need to be different letters here. So we're going to use this right one here, and this gives us, if we subtract the a over, 1 minus a, not 1 minus, we're subtracting the a over, 1 equals np minus a. And then using this for a, we have this equals np minus mp, and we got that prime sitting there that we can factor out, n minus m. So now we have that 1 equals p times n minus m. And we know, since n and m are in z, n minus m is in z. And p, since it's prime, our definition of prime, what are we doing? P must be, ooh, that's a must. Let me write that a little bit bigger for you guys. Must be 0, not 0, it's prime. What am I doing? 1 less than p less than or equal to nothing. Well, we can do nothing here, because 1's not prime. So those of you who are taking linear algebra, you'll be familiar with the concept of units. 1 is our multiplicative unit in regular arithmetic. So if you're prime, we say 1's not prime. So that means if we have a prime, it has to be bigger than 1. Well, regardless of what this is an integer, and this statement here, combining this, is saying that we know that and p divides 1, which is a contradiction. Nothing divides 1 except 1 and negative 1 in the integers. So that's our contradiction. Or, you can think of it, n minus m could equal 1. So put another way, we know that p is greater than 1, and if this expression, n minus m, was to equal 1 for some reason, because that's the only other case outside of what we've already said here, it would be p is greater than 1 and p equals 1, which is, still a contradiction. Oh, I should have wrote bigger there, sorry. Right, but that's p greater than 1 and p equals 1. So therefore, it must be the case that if p divides a, then p does not divide a plus 1. That's our proof. So, sorry, I'm pausing. I'm still used to waiting for questions. So now we can go back and we're going to have to use this property to prove this theorem. So property, proposition, same but different if you're in the textbook following along. So this is going to be the proof for the set of primes is infinite. Primes is infinite. Yeah. So classically, I'm going to suppose not. That is, suppose the set of primes is finite. So, if the set of primes is finite, that means that there has to be a largest and a smallest. Now we know that there is a smallest prime, it's 2. So what we really want to key in on here, in fact, is that this means that then there is a largest prime. And so then there exists some p in z that is prime, and p is greater than or equal to n greater than or equal to n. Gotta fit this in nicely here. Scoot my stack of papers down. That'll work. So this is where n is any. How dare you, paper? Stay up there. Any other prime. Okay, because that's what it means to be largest. So what we're going to do now is look at all of the primes. So now we're going to let this capital N equal 2 times 3 times 5 times 7 times 11 times ... all the way down to p, the largest prime. So we're going to construct a very, very large integer. And then we're going to add 1. So n is this thing plus 1. Or the product of all prime numbers plus 1. So, since n is certainly greater than 1, there exists a q in z such that q is prime. And q divides n. Every integer can be factored in the prime. So this is that fundamental theorem of arithmetic that we talked about. This would have been 2 weeks ago now. So since q is prime, q must equal must. It's weird to write this big. I'm working on it, guys, I promise. Q must equal 2 or 3, 5, 7, 11, ... or p. Right? It has to. Because it's prime, and p is the largest prime. So if q is another prime, it's one of the primes. And so q divides 2 times 3 times 5 times ... all the way to p. And by the previous problem, q does not divide 2 times 3 times 5 times ... times p plus 1. Or in other words, Q does not divide N. And you can't see everything that I just wrote. So there it is. I'll repeat. So our previous problem was showing that if something divides something, it definitely doesn't divide the next integer. And so since Q is prime, it has to divide the product of all primes. And then we can induce that problem to know that that definitely can't divide the product of all primes plus 1, which is N. But we know that Q was specifically a prime that divided N by N, or divided into N. So this is, of course, with this and this, a contradiction. Contradiction. Can I spell that? Yes. And therefore, so it must be the case that there is no, speed that up, largest prime. And that's the end of the proof. Now, some of you might be wondering, well, we made more than one assumption. I made a big gripe about not making more than one assumption last week. And you're probably thinking about it right here. Right? So this is not an assumption. If n is an integer, which it is, then there exists a prime that divides it. Now, since the specific construction of n here, if a prime divides it, it's a prime. So it has to fall into the product of all primes. It has to be one of these. And if it is, then it has to divide the product of all primes. And then that's why we needed that other problem. So that is the end of 4.7. These are good proofs to have seen. They'll help you in the homework, not necessarily do proofs. You'll use the two theorems here, the irrationality of the square root of 2, and the fact that primes are infinite in at least a couple problems. But the big thing here is just seeing different styles of proof. Stuttering there. So yeah, we're going to end there. And the next video will be the start of chapter 5. No, it'll be 4.8 because I'm covering 4.8.